Good afternoon, everyone. Thank you for joining us to talk about the 3D project. I'm Thibaut Bentley from Greenflex, working on this project for 5 years. Thank you for your interest in this 3D project. The 3D project, it stands from DMX Demonstration in Dunkirk, and well, it's part of an Horizon 2020, the European Union's Research and Innovation Program, and it started 5 years ago, and this project is coordinated by IFPEN, and it wants to bring together many partners of many countries from 6 European countries, including ArcelorMittal, Axens, Total Energy, and here. Today, we're here to talk to you about this innovative process for capturing CO2. It's a CCUS project on industrial activities, and it's working with the DMX project. And here we've spent 5 years working on this project on the ArcelorMittal site in Dunkirk, and today we're ready to share some main results of the DMX technology today. And I'm here with Martin Pfeiffer. He's a lead technology engineer at Axens, and he's going to present the main results of the DMX. I'm also here, I have the pleasure to be with Vania, Maxime, and Clément. Their work at Axens or IFPEN, and they've managed a few of the aspects of the 3D project. And after Martin's talk about the main results, they'll answer your question if you have any about the project, the stakes, and what will be done after the project. So I'm very happy to let the floor to Martin Pfeiffer. He will present the main results of the DMX.
So let's start. So as you know, if we want to reach net zero emission by 2050, we need to reduce drastically our CO2 emissions globally. And as stated by IPCC, there are several ways to do so, such as energy efficiency, switching to renewable fuels, and deploying massively CCS projects. In this regard, Axens and IFPN have been working on developing a post-combustion carbon capture process called the DMX process since 2010. As part of the development of this technology, we have been awarded this 3D project in order to demonstrate the technology. As part of this 3D project, we constructed and operated a pilot.
I'm sorry, it's freezing. We have only the first slide.
Yeah, actually, I'm still on the introduction.
Okay, thank you. Thank you.
And during today's webinar, I will give you introduce what is the DMX process, and I will give you the results of the operation of the pilot in Dunkirk. So first, a few words about Axens. So I'm working as a lead technology engineer in Axens, and Axens will be responsible for the commercialization of the DMX process. So Axens provides technologies as well as products, services, and equipment for different markets in oil refining, petrochemical historically, but also in new domains such as water treatment, biogas, and also in the carbon capture, utilization, and storage. So Axens headquarters is in Rueil-Malmaison near Paris. There are more than 2,000 people working at Axens in 15 offices. So we have sold more than 3,000 units under license. Each year we sell 75,000 of catalysts and adsorbents, which are manufactured in our 7 factories around the world. And we also sell modular units and heaters. So now let's jump to let's jump to today's topic, which is the DMX process. So the Accents and IFPN has been working on the development of this post-combustion carbon capture process using cutting-edge technology solvent, which has a capability to demix under specific operating conditions of CO2 loading and temperature. So the demiction is the separation of the solvent under two different phases, a CO2 lean phase and a CO2 rich phase. So the CO2 lean phase will not contain the CO2, while the CO2 rich phase will contain most of the CO2. So now you understand the principle of the demixing. Let's jump to the schematic on the left, which is the simplified PFD of the DMX technology. So the solvent, the flue gas which contains the CO2 that need to be removed will enter an absorber countercurrent, and it will be under countercurrent in contact with a lean solvent, which will capture the CO2. At the top of the absorber, we have the treated gas from which the CO2 was removed, while at the bottom of the absorber, we have the rich solvent from which the rich solvent containing the CO2 that was captured. The rich solvent is then routed to a decanter where the key of the process occurs in the decanter, where we have the demiction that I just described previously. So as you can see on this schematic, we have the separation of a CO2 lean solvent phase and a CO2 rich solvent phase. The CO2 lean solvent phase is routed back directly to the absorber without being regenerated. So basically, it's self-regenerated by the demiction. While in the CO2 rich solvent phase is routed to the stripper for regeneration. So we provide some heat to the stripper, for instance, by providing steam to the reboiler. And at the top of the stripper, we have CO2, a pure CO2 stream recovered. The lean solvent is routed after regeneration. The lean solvent is routed back to the absorber for another cycle of absorption. The key here is the decanter. This is the key of the process, so it will allow to have part of the solvent bypassing the stripper, which will allow to reduce the energy consumption. So for another amine processes using a non-demixing solvent, such as any process, all the rich solvent will be routed directly to the stripper. So you will have more or less the same scheme, but without this decanter. There are several benefits of the DMX solvent. First, of course, it is demixing capability. Then it has a very low energy consumption. It is thermally stable, which means we can operate the stripper at a relatively high temperature, up to 150 degrees, which allows to produce a CO2 stream under pressure of up to 5 bar gauge. This solvent is also very low sensitive to oxygen, which means it has low degradation product formation, and it can reach high capture rate, up higher than 90%. And finally, we have a high purity of the CO2 produced, up to 99.8% in dry basis. The DMX process has been developed in order to be a versatile process, which means it can be applicable to a wide field of application with varying flue gas quality, wide range of CO2 concentration, and it can handle wide range of flue gas flow rates. So it can be applicable to many industries such as cement, lime, steel, aluminum, paper, power generation, and so on. So in the end, DMX technology will be applicable to your own application, and you can see that the DMX process is applicable to any type of industries. So after this reminder about the DMX technology itself, let's move to the 3D projects. As Thibaut mentioned, 3D stands for DMX Demonstrator in Dunkirk, and it's a project funded by the European Union. The purpose of this project is twofold. First is to demonstrate the technology, the DMX technology itself, with the construction and the operation of a demonstration unit, which has a capacity of 0.5 ton of CO2 capture per hour. This unit, which was delivered by under module by Axence, is connected to ArcelorMittal blast furnace gas network, and it's located in Dunkirk, in the steel mill factory from ArcelorMittal. This is the first objective, which is a demonstration of the technology, and the second objective is to perform a pre-feed of the complete CCS chain for 1 million ton CO2 capture plant and CCS chain from ArcelorMittal emitting point toward the storage location in North Sea. So as I mentioned, the first objective of the 3D project is a demonstration of the DMX technology with construction and the operation of these pilot plants. So the construction started in 2019, and the project started in 2019, and the pilot started up in 2023 and has been in operation for the last 2 years. It has a design capacity of 0.5 ton of CO2 per hour, as I mentioned, and it will treat ArcelorMittal blast furnace gas with the possibility to tune the inlet CO2 concentration thanks to dedicated recycle lines. The second objective is the pre-feed of a full carbon capture chain of a 1 million ton CO2 capture per year. So the first point will be to design a DMX unit for this 1 million ton of CO2 capture per year capacity. This is what we call the work package 3 later on. And as part of this pre-feed, we have also heat recovery from steam mill plant, CO2 conditioning and liquefaction, CO2 transport to North Sea offshore storage location, and its social acceptability of such a project. There will be also development of a CCL industrial cluster in Dunkirk area, and the main partners involved are listed here. So we can mention especially IFP Energy Nouvelle, who is leading this project, ArcelorMittal, Total, and Axence. So let's move more in detail about the pilot itself. So here you have a photo of the pilot. So it's connected to the blast furnace gas network from ArcelorMittal, and here on the left I have the typical gas composition of this blast furnace gas. So we can notice that we have, as per design, 25% of CO2, 23% of carbon monoxide, some traces of hydrogen and oxygen, a lot of amount of nitrogen, and some contaminants such as H2S and COS. So the purpose of this pilot will be to treat this gas and to test different operating conditions by varying the pressure, temperature, flow rate, CO2 composition, and so on. So here are some key values. So on this platform, you can see on the picture, you have the absorber and the regenerator. So typically, the column height is about 70 meters. For the different tests, we will be able to vary the pressure in the absorption between 0.2 and 1.8 bar gauge. The regeneration pressure will be between 2 and 5 bar gauge. We'll be able to vary the flue gas flow rate between 200 and 1100 normal cubic meter per hour. The CO2 concentration as per design is 25%, but with some dedicated recycle lines, we can vary it between 12 and 30%. The solvent flow rate has a range between 2.5 and 7.5 ton per hour. and the nominal capacity of the plant is to capture 0.5 tons of CO2 per hour, with a capture rate higher than 90%. So now let's go more in detail about the demonstrator itself. So you have three main sections: the absorption section, where the flue gas is in contact with the lean solvent. This is where the absorption will take place. There is the decanter, where the demission will occur and will produce the lean CO2 organic phase and the rich CO2 aqueous phase. And on the right side, you have the regeneration section, where CO2 will be produced and routed to AMF network. AMF stands for ArcelorMittal France. And as an input, we have some MP steam from AMF as well. So as part of this R&D demo plant, there are several features which are key for the demo plant. Upstream the absorber, there is a gas conditioning package for filtration and pressure and flow rate control. As absorption reaction is exothermic, we provided a solvent intercooler in order to maximize the absorption capacity, which means that we withdraw all the solvent at the middle of the tower, we cool it down and we re-inject it. At the top of the absorber, there is a dedicated water wash section to limit solvent and VOC emission. For this pilot, in order to test the injection at the impact of the packing height, we have the possibility to inject the solvent at different packing heights. That's why here you can see that we have a multiple injection point to the absorber. There is a simple heat recovery for this pilot with a lean-rich solvent heat exchanger. It means that the cold, rich solvent is heated up by the hot lean solvent before being routed to the decanter. And last but not least, in order to be able to modify the CO2 composition at the inlet of the absorber, we have different recycle lines. So we can either recirculate the pure CO2 if at the inlet of the absorber if we want to increase the CO2 composition, or we can recycle the treated gas if we want to reduce the CO2 concentration at the inlet of the absorber. So this is a picture of the overall plot plant related to the pilot. So it's already quite a big demo plant, as you can see on this picture. So on this platform, which is about 26 meters high, you have the absorber and the regenerator. Here you have the decanter, as well as some other packages, such as the compression package, the refrigeration package, and this building is a control room. So this will give you a nice overview of how big is a 0.5 ton per hour CO2 capture plant. So now let's move to the results. The purpose of this demo plant, of course, is to demonstrate that the technology operates well. And also, it will help us to provide solid evidence that will answer all the challenges we are facing for the industrialization of the process. So we'll look at process operability, energy penalty reduction, solvent degradation management, solvent and VOC emission at the top of the absorber, what is the purity of the produced CO2, R&D data production, as well as corrosion impact. So first, let's start with process operability. We can definitely say after 2 years of operation that we successfully operate the DMX process using a demixing solvent. We did not observe any solvent foaming in the columns. We have not observed any unexpected solvent composition deviation. And very importantly, the demixing occurred as per expectation in the decanter. So we have here, you can see on this graph a representation of the different flow rate from and to the decanter. So in red, you have the total flow to the decanter. And in blue, you have the evolution of the flow rate from the decanter of the rich CO2 phase, which is routed to the regenerator for regeneration. And in pink, you have the production of lean CO2 phase, which is routed directly back to the absorber. So we can see that it's very stable, and the lean solvent, the lean CO2 phase is about 15 to 20% of the total flow routed to the decanter. In total, the pilot plant has been operated about 5,000 hours in capture mode, meaning with gas and liquid flow rate together. We have been performing more than 100 parametric tests. For the different parametric tests, we have varied the CO2 composition, the temperature, pressure, gas and liquid flow rate, and so on, in order to accumulate a lot of data to test the behavior of the unit under these varying operating conditions. And all this information will be fed to our absorption model in order to make it more robust. So we can say that during those 5,000 hours of operation, we have not observed any operation issues related to the DMX technology itself. However, we can mention that, of course, we had some small operation issues, which is not directly related to the technology itself, but to the design of the demonstrator. For instance, we had several loss of measurement in the column, which led to some trips. So it was related to the level indicators. Or we had some limited capacity of the gas filtration in the compression package. We also led to some trips, but these are not related to the process itself. So what did we test during those campaigns? So as we said, we performed more than 100 parametric tests, and we tested different CO2 partial pressure, which represent different type of industrial applications. So we performed some tests at 0.15 bar CO2 partial pressure. It's in order to simulate coal power plants with 12 to 15% CO2. We simulated some blast furnace gas application at 0.2 bar gauge with a CO2 partial pressure of 0.3 bar. Also some tests at 0.6 bar to represent blast furnace gas application at 1.8 bar gauge. And also an application for ArcelorMittal at 1 bar CO2 partial pressure. So in total, we have more than 100 tests, and this is the distribution of those tests. So you can see that they are more concentrated around blast furnace gas application. So that's cover the process operability section. So let's move to the energy penalty reduction now. So on this graph, I plotted the energy penalty with a 100 basis as a function of the CO2 partial pressure for some different tests that we performed. So we can see, of course, a decreasing tendency when we increase the CO2 partial pressure. And for instance, we have a 25% reduction of the energy penalty when we increase the partial pressure from 0.2 to 1 bar absolute. So we have a low energy penalty in the DMX for the DMX process, as demonstrated with the 3D pilot. And for an industrial unit, when we go for industrial design, we will have additional significant reduction of energy penalty with optimized thermal integration within the process itself and with optimal column height. So that section covers energy penalty reduction. Now let's move to the solvent degradation management and what we observed in the pilot. So as I mentioned, we perform more than 100 tests, and for each test, we follow up the composition of the lean solvent by a gas chromatography analysis in order to measure the composition of unknown compounds in the solvent. You have to keep in mind that at the beginning of the project, the solvent degradation target was to be below 5% of the total inventory per year. During this, all the tests, the temperature at the bottom of the regenerator varied between 120 and 160 degrees with an average of 140. And also keep in mind that for the blast furnace gas application, there is a high content of carbon monoxide, about 25%, as well as the presence of other degradation promoters, even if in low quantity, such as NOx, SOx, and oxygen. So on this graph, I plotted the temperature at the bottom of the regenerator, which is the hottest point in the process. So you can see that the average temperature is around 130 to 140 degrees. So these are the red dots. And if you look at the black dots, it corresponds to the evolution of the composition of unknowns in the solvent. And you can see that it has an increasing tendency starting from 0 and reaching 0.58% of unknowns after 5,500 hours of operation. So we can say that we have at 3D a very low degradation rate, as we reach 0.5% of the inventory after 5,000 hours. And if we convert this in another unit, it represents losses due to degradation represents less than 0.02 kilogram of solvent per ton of CO2 captured. So in addition to unknown components, we also observe some heat. We also monitor heat stable salt formation in the solvent. So here differently, we perform once per month some analysis by unique. We analyze unique chromatography of the solvent once per month. So we can observe that we have from beginning formiate production, which reach an equilibrium ranging between 1,000 and 1,200 ppm weight of formiate. And if we perform a zoom in the y-axis, so the below graph is the same graph than the one above, but we have a zoom on the y-axis between 0 and 100 ppm, we can notice that we also have a small formation of acetate, sulfate, and nitrates. But this remains very low and below 100 ppm after 5,000 hours of operation. So the degradation is very low and is under control. So this is what we wanted to show you regarding the solvent degradation at 3D. So now let's move to solvent and VOC emission. So at 3D, we can perform online gas analysis with FTIR and micro-GC for the main product. So for the main component of the gases, but also we can measure NOx and SOx as well as VOCs. We can also perform some offline analysis campaign, one for sulfur components by a third company named Lesses, and also for VOC compounds, we perform a campaign by Ineris. Now I'll present the typical result we observe for the blast furnace application for the emission in the treated gas. So we measure below 1 ppm of oxygenated compound in the treated gas. So it means at the top of the absorber. We did not detect any alkanoalamines, And regarding the amines, we measure below 4 ppm of DMX, below 2 ppm of NH3, and below 1 ppm of other amines. But very importantly, you have to keep in mind that for the demo plant, the 3D washwater system at 3D is very simple and without recirculation, while for industrial units, we will go for a more sophisticated design, which will have a much higher efficiency in order to reach this 1 ppm target for the emission of amines in the treated gas. And regarding the offline campaign, we measure very low concentration of aldehyde and amines, and we did not see any nitrosamines. Sorry. So we have very promising results. So now let's move to the purity of the CO2. Very important question is, does DMX process meet CO2 specification? So as you know, the CO2 specification will depend on the storage site and transport strategy. So for 3D project, we looked at Aramis and Northern Line spec. Keeping in mind that Northern Line spec is very severe. So for the specification, we looked at inert, presence of SOx and NOx, sulfur compounds, and VOCs. So on this table, I provide you the typical CO2 composition for blast furnace application at 3D in comparison with Aramis spec and Northern Line spec. So for the CO2 purity, we have in wet basis 99.1%, and we have a presence of moisture at about 0.7% under those conditions, which means after drying, after removing the water, we will definitely reach a spec of 99.8% in dry basis of the CO2. Due to the co-absorption of some inerts, such as nitrogen and carbon monoxide, we measured 1000 ppm of nitrogen and 700 ppm of carbon monoxide. So in order to reach Northern Lights specification, additional polishing will be required. And as part of the 3D project, liquefaction step was included as another work package. So it was done by Air Product in order to meet CO and N2 specification at the outlet of the CCS chain before storage. If we look at the sulfur compounds, we do not have an issue with SOx. However, as there are some H2S present in the gas to be treated, this H2S will be absorbed along with the CO2 and will be released in the CO2 stream. So at 3D, with given the H2S content in the blast furnace gas, we measure 37 ppm of H2S in the CO2 stream, which means a post-treatment will be required to meet Aramis or Northern Lights spec of 5 and 9 respectively ppm. This will be included in another work package, and typically dedicated adsorbent can be proposed to meet this specification. And regarding VOCs, we don't have any issue with amine or formaldehyde and acetaldehyde or NH3. So it's very promising results in view of transport and storage. We can mention that at the outlet of the DMX process, we have a very pure, we can produce CO2 with a very high purity, more than 99.8% in dry basis. However, the specification for each project will depend on the storage site and the transportation mode. So you will need to adapt your conditioning unit depending on the specification you are targeting. keeping in mind that if your specifications are too tight, it will have big impact on your capex and opex, and it could even jeopardize your project. So this covers the purity section. Let's move to R&D data production. So as you all know now, at 3D we perform more than 100 parametric tests in which we modify the different operating conditions, CO2 composition, temperature, pressure, flow rate, and so on. And for all those tests, we perform consolidation and reconciliation of the mass balance in order to be able to accumulate a lot of information about those tests and be able to feed them to our absorption model in order to continuously update it with all the 3D consolidated results, which allow us to have a very strong and robust simulation tool. So I would like to thank IFPN hard work on that to provide Axence a robust simulation tool, which will be used for industrial design. So now I will show you what are the output of this simulation tool. So here I plotted the temperature profile along the absorber for a blast furnace gas application at 0.2 bar gauge. So in the blue line corresponds to the temperature profile of the gas, while the red line corresponds to the simulated temperature profile of the liquid. And you can compare it with the blue and red square, which correspond to the actual measurement at site with the thermocouples. So we can see that we have a good match between the simulated data and the experimental data for this test. And if we look at the capture rate, the black line, this is the evolution of the capture rate along the absorber. So we have 0% at the bottom and about 90% at the top. So the line corresponds to the simulated capture rate, while the black square corresponds to the experimental data. So at 3D, we can measure the capture rate at the top of the absorber as well as at the middle of the absorber with a dedicated gas analyzer. So again, we have a good match with between the simulated data and the experimental data with very low uncertainty. And also we can mention that the results from the simulator are a little bit conservative. And now if I plotted the same graphs for another application, blast furnace gas at 1.8 bar gauge. So again, temperature profile along the absorber, which is also a good match between simulated data and experimental data, and the evolution of the capture rate. So again, we can mention and we can conclude that the simulator results are in a good agreement between the experimental data and the simulated data, and this for all CO2 capture application. So now in Axence, we have a very robust simulation tool in our hands to perform a design for industrial application. So now let's move to corrosion impacts. So this is the simplified PFD that you've already seen about the pilot. So we early in the design, we installed some corrosion coupon at different locations in the unit in order to monitor the corrosiveness of the solvent under different operating conditions. So here we have one to measure the corrosivity at for the cold rich solvent, also for the hot rich solvent, for the CO2 rich phase, for the hot lean solvent, and also at the semi-rich in the intercooler. So all these coupons were in contact with the solvent for more than 4,500 hours of operation, And the conclusion is that we have very low corrosion rate for carbon steel, below 5 micron per year, and almost no corrosion for stainless steel, which confirm our material selection strategy to have part of the unit in carbon steel. Whereas, for instance, if you have a MEA process, all the equipment will be in stainless steel. So this covers all the main challenges. Thanks to the 3D pilot, we have been able to check and analyze and overcome all the DMX development challenges. How I present it to you. So now let's have a few words about the industrial unit. So as you know, as part of this 3D project, Axence designed a DMX process for ArcelorMittal for 1 million tons of CO2 per year. So we did the first design in 2021 based on our knowledge at the time. And as part of the 3D project, it was foreseen to have an update of this case, which we call the work package 3, based on the outcome of the demonstration. So in 2024, we did an update of this work package 3 in order to highlight improvement and change made on the DMX technology based on our knowledge in 2024. Here I remind you quickly what are the design value for this case, which is very similar to the composition for the design of the pilot. And regarding the improvement we made for work package 3 update, of course we used the updated simulation model given by IFPN, which was updated based on the demonstration results. We proposed the optimized scheme regarding the heat integration. We optimized the absorber design with 2 intercooling steps and also with a higher packing bed in order to reduce the solvent flow rate, which helps this reduction of solvent flow rate help us to downsize the regeneration section and to minimize the size of the decanter. Now we'll give you some comparison results between 2021 case study and 2024 update. So we can see that we have a decrease in energy consumption by 28%. We managed to reduce the solvent flow rate by almost 40% for an equivalent capex. And the OPEX is also decreased by 40%. So with this 2024 work package 3 update, we have a significant reduction in solvent flow rate and energy consumption. So now it's time for the conclusion. So we can definitely say that we have a successful operation of the DMX process at Dunkirk. Using a demixing solvent, the energy penalty at the pilot matches the initial target. And beyond that, we can have a significant reduction of energy penalty for industrial unit using optimized heat integrated scheme with an optimal absorption height in the absorber. As you have seen, we have the DMX solvent has a good resistance to high temperature and leads to low production of HSS, so the degradation of the solvent is under control. We have very low VOC emission in the treated gas. The DMX process allows to produce a very high purity CO2, and there is no trace of corrosion for the metallic coupons. And last but not least, thanks to the hard work done during these 2 years of operation, we have now a good simulator coupled with a high reliability of experimental data, so we have a robust simulation tool in our hands in order to perform any design for you. So now we can say that the DMX is environmentally responsible, demonstrated, and can be applied across all industries. Thank you for your attention, and we'll be happy to answer your question now.